Now let us solve the system given here. So we will have 4 equations in 4 unknowns. So the first thing that we need to do to solve the system of linear equation is to form the augmented matrix, right? So we simply get all the coefficients of the variables x sub 1, x sub 2, x sub 3, and x sub 4 being 0, 1, 2, 1. And then you also have here your 1, 2, 4, and negative 4. And okay, what else? We have here for your third column, you have 1, negative 1, 1, and negative 7. And then you have negative 2, 0, negative 3, and negative 1. And finally, the last column being the constant terms. So again, in order to apply the Gaussian elimination, we will be applying the 3 elementary row operation. That is, we can interchange rows. We can multiply a row by a constant, and we can also add, let's say, a multiple of a row to another row. So notice that in our augmented matrix, we do not have the leading one. So since the second row has 1 as the first entry, what we can do is to interchange row 1 with row 2. So we have it here. Interchanging row 1 with row 2 gives us an entry in row 1 as 1, and we will have 0 below it. Okay, so we have 1 to negative 1, 0, 2, and then we have 0, 1, 1, negative 2, negative 3, and the third row will start at 2, and the fourth row will start at 1. Now we need to convert 2 and 1 to 0. So what we can do now is to multiply row 1 by negative 2 and add it to all the entries in row 3 to form the new third equation, to form the new third row. So here, if I multiply this by negative 2 and add it with row 3, we have negative 2 plus 2, we have 0. Negative 2 times 2 will be negative 4 plus 4, that will be 0. Negative 2 times negative 1, that will be positive 2. 2 plus 1 is equal to 3. Negative 2 times 0 is 0 plus negative 3. We have negative 3, and negative 2 times 2 is negative 4. Negative 4 plus negative 2 is negative 6. Now, we already have a 1, 0, 0 here. We need to convert this to 0. And we can still use row 1. Say if I multiply row 1 by negative 1 and add it to all the entries, say negative 1 of row 1, adding that one to all the entries in row 4, we have negative 1 plus 1, this will be 0. Negative 1 times 2 is negative 2. Negative 2 plus negative 4 will be negative 6. Negative 1 times negative 1 is positive 1. 1 plus negative 7 is negative 6. And negative 1 times 0 is 0 plus negative 1. We have negative 1. Negative 1 times 2 is negative 2 plus 19. Negative 19 is negative 21. So this one, we were able to have a good start. So we were able to convert all the numbers below 1 to 0. And we will have here the next leading one, which is the coefficient of the second variable. Now, since we already have a 0 below it, then we only need to convert negative 6 to 0. So what we can do here is, if we can use our row 2, say multiply row 2 by 6 and add all the entries in row 2 with the entries in row 4. So what will happen? So if we do that, say, okay, so let's say we multiply the entries of row 2 by 6 and add it with the entries of row 4. We have 6 times 1 is 6 plus negative 6. This will be converted to 0. 6 times 1 is 6 plus negative 6. This will be converted to 0. And 6 times negative 2 will be negative 12. Negative 12 plus negative 1. That will be negative 13 now. And 6 times negative 3 is negative 18. Negative 18 plus negative 21 is negative 39, right? So this will be the new entries for your row 4. Now let us see the next slide. So we have here 1, 0, 0, 0, and then we have 2, and then we have changed all the numbers below the next leading one to 0, and we have for the third row we have 3, negative 3, and negative 6, and for the fourth row we have 0, negative 13, and negative 39. Now we can actually simplify row 3. Say if we multiply row 3 by 1/3, okay, then this one becomes 1. Negative 3 times 1/3 becomes negative 1. And we have negative 6 times 1/3 becomes negative 2. And then we already have a 0 below that one. So see here that we have the first leading one at the topmost left corner, and then below that one are all zeros. And then we will have the next leading one as this, which is the coefficient of the next variable, and below that one are all zeros. And then we find the third leading one here, and below that one is also 0. And then we find the next leading one, which is this. Consequently, we know what the last row means. It simply means that we will have the last variable, which is, okay, can we go back? Is it x sub 1, x sub 2, x sub 3, x sub 4? Let me just check. Yeah, okay, so it's understood according to the last row that we will have 1 times x sub 4 is equivalent to 3. Okay, so that row 4 simply tells us that x sub 4 is equivalent to 3. And we can now apply our box substitution to solve for x sub 3. And then once we know x sub 3, which is simply negative 2 plus 3, which is positive 1, we can now apply box substitution again to find x sub 2. And once x sub 2 is obtained, we can now find x sub 1. Now let's see what are the answers. Okay, so we have here x sub 4 is 3, x sub 3 minus x sub 4 is negative 2, x sub 2 plus x sub 3 minus 2x sub 4 is equal to negative 3, and you will have x sub 1 plus 2x sub 2 minus x sub 3 is equal to 2. Okay, applying the box substitution, we can see now that the solution is contains the following coordinates. We will have negative 1, positive 2, positive 1, and positive 3. And since we only have one solution, the system is said to be consistent independent. Now, what about for Gauss-Jordan elimination? What makes this different from Gaussian elimination? With Gaussian elimination, you apply elementary row operation to a matrix to obtain a row equivalent row echelon form. A second method of elimination, called Gauss-Jordan elimination after Carl Friedrich Gauss and Wilhelm Jordan, continues the reduction process until a reduced row echelon form is obtained. Example, use Gauss-Jordan elimination to solve the system is actually the same thing as the problem that we had earlier. So using the same problem, x minus 2y plus 3z equals 9, negative x plus 3y equals negative 4, 2x minus 5y plus 5z is equivalent to 17. So again, we form the augmented matrix. So we have here 1, negative, okay, so since we know that the Gauss-Jordan elimination is just a continuation of the Gaussian elimination, we will already have the row echelon form from the previous problem, which is given by 1, 0, 0, negative 2, 1, 0, 3, 3, 1, and 9, 5, 2. Now, to find the reduced row echelon form of this matrix, we have to perform what you call a backward process. So here we need to convert, okay, since already have the leading ones, what we need to do is to make this 0, to make this 0, as well as to make this 0. Now, how do we do that? So the first thing that we can do is to simplify or to convert, to transform to 0, okay, this entry which is -2. And how do we do that? We can actually make use of row 2. So say, if I multiply row 2 by 2, say twice of row 2, and add that one with row 1 to be our new row 1, what happens? Okay, so we have 0 times 2 is still 0 plus 1. Okay, 1 is maintained. 2 times 1 is 2 plus -2. This becomes 0. 2 times 3 is 6 plus 3. This becomes 9. And 2 times 5 is 10. 10 plus 9, this becomes 19. So let us check our answer. We have 0. Okay, you have 1, 0, 9, and 19. Now, we already have this to be 0. The next thing is to convert this to 0. Now, what we can do is we can use row 3, right? We can use row 3, say multiply the last row by -3 and add it to row 2. Say here, -3 times row 3. So let us multiply row 3 by -3. Sorry. So since we have it here, multiply row 3 by -3 and add it with row 2. So say -3 times 0 is 0 plus 0 is still 0. -3 times 0 is 0 plus 1, it is still 1. -3 times 1 is -3 plus 3 becomes 0. -3 times 2 is -6. -6 plus 5 is -1. So this will be the new second row. Okay, looking back, let us check here. You will have the leading one, and below that one is 0. Okay, below that one is 0, and we have the last leading one. And above those leading ones should be 0. So here we have above 1 is 0. Here above 1 is 0. And we still need to convert this to 0. So what we can do is we can choose to multiply row 3 by -9 and add it to the entries in row 1. So this becomes 0. So -9 times 0 is 0 plus 1 is 1. -9 times 0 is 0 plus 0 is 0. -9 times 1 is -9. -9 plus 9 is 0. -9 times 2 is -18. -18 plus 19 is equivalent to 1. So notice that we were able to come up with reduced row echelon form. So in a reduced row echelon form, what do we have? We were able to convert the coefficient matrix such that the entries in the diagonal are only ones, and above that one and below and above that one are all zeros. Consequently, we can interpret the reduced row echelon form of the matrix in terms of the solution. So we will have here Z is equal to 2. We have Y is equivalent to -1. And we will have X equivalent to 1. Okay? So you have 1, -1, and 2. Now, another type of system of linear equation is the homogeneous system of linear equation. A system of linear equation in which each of the constant term is 0 are called homogeneous. A homogeneous system of m equations in n variables has the following form. So we have an m number of equation in n unknowns wherein the right side are all zero. This is a system of linear equation or homogeneous system of linear equation. Now, a homogeneous system of equation must have at least one solution. Specifically, if all variables in homogeneous system have the value zero, then each of the equation is satisfied, right? So let's say x sub 1, x sub 2, x sub 3, up to x sub n are all zeros, then it will satisfy every equation in the system. We will refer to such solution as the trivial solution. Okay, so if all variables in homogeneous system have the value zero, then each of the equation is satisfied and such solution is called the trivial solution. Example, solve the system of linear equation. We have three unknowns in two equation. So we form now the augmented matrix, isolating the coefficient matrix as well as with zero. And then we need to convert this to zero, of course. So say multiplying equation 1 by -2, and then multiply row 1 by -2 and add it with row 1. Then what happens? So what happens if we multiply row 1 by -2? Row 2 becomes, so -2 plus 2, this becomes 0. -2 times -1 is +2. 2 plus 1 becomes 3. 3 times -2 is -6 plus 3. This becomes -3 and 0. So we will have the new matrix, which is 1, -1, 3, 0, and 0, 3, -3, and 0. Okay? Notice that we can still simplify the last row by multiplying both sides by, say, 1/3. So we will have 0, 1, -1, and 0. And for row 1, we will have 1, -1, 3, and 0. Obviously, we can interpret now, or we can still proceed with the elimination process so that we can come up with a reduced row echelon form. So we need to convert this to 0, say adding row 1 with row 2. So to be the new row 1. So we have 0 plus 1 is still 1. And then 1 plus -1, that will be 0. -1 plus 3, that will be 2. And then 0. So you'll have 1, 0, 2, 0. And then 0, 1, -1, 0. Now, obviously, we can interpret the reduced row echelon form of the matrix as, so this means that the coefficients of column 1 are coefficients of x. For column 2, the entries are coefficients of y. For column 3, this is a coefficient of z, or coefficient of x sub 1, coefficient of x sub 2, coefficient of x sub 3. Now, with that one, we can interpret this as x sub 2 minus x sub 3 is equal to 0. And then for row 1, we will have x sub 1 plus 2x sub 3 equal to 0. Now notice that since, what do we notice? How do we find the solution? So since there are more unknowns than the number of equation, we will be using the parametric representation, right? So based on this equation, do we need to represent it parametrically? Because according to row 2, we will have x sub 2 is simply equivalent to x sub 3. And what about x sub 1? X sub 1 is just equivalent to -2 x sub 3. Now, if we let the free variable to be x sub 3, say let x sub 3 be a parameter t, such that t is any real number, then we can find the solution set for this system of equation as we will have x sub 1 to be -2t, and x sub 2 is just equal to x sub 3, and x sub 3 is t. So we have negative 2t, t, as well as t. Now you can assign any value for t, since t can be any real number. So again, if we say that t is equivalent to 1, then that means x sub 1 is negative 2, and then we have 1, 1. So we can test it here, say negative 2 plus 2 is 0. Okay, and then again, if t is equal to 1, then we have negative 2, 1, 1. Negative 2, we don't have x sub 1 here, but we have t to be 1, and 1 minus 1 is also 0. Okay, so again, we have here the use of the parameter to represent x sub 3, so that the solution set is simply given by negative 2t, t, and t. Of course, if t is 0, then we will have the trivial solution. We come up with 0, 0, and 0. So for theorem 1.1, which is about homogeneous systems of linear equation, the number of solutions of homogeneous system, or it gives us the number of solutions for a homogeneous system. Every homogeneous system of linear equation is consistent. Moreover, if the system has fewer equations than variables, just like what we did earlier, then it must have infinitely many solutions. Okay, so that will be all about the Gaussian and Gauss-Jordan elimination, which is a method in solving a system of linear equation. Now again, going back with Gaussian elimination, we simply apply the elementary row operations, being interchanging rows, adding a constant, multiplying a constant to a row, and adding multiples of a row to another row will allow us to transform a system of equation into row echelon form. Now, if we continue on with the process, okay, that means we are performing a backward elimination, such that all the leading ones in the row echelon form will have zeros on top of them, okay, referring to the coefficient matrix. So we will refer to that process as your Gauss-Jordan elimination. So with the Gauss-Jordan and Gaussian elimination, we can solve the system of linear equation. Another type of system of linear equation is the homogeneous system of linear equation, wherein the right side are all zeros. Here, we can see that one of the solution is the trivial solution, because for all values of, if we have x sub 1, x sub 2, up to x sub n be 0, then it will definitely satisfy the equation, which is equal to 0. Now, if there are more unknowns than the number of equation, then the system will have infinitely many solutions, and the solution can be given by a parametric representation. Okay, so that's all about today. In the next topic, we will be discussing some of the application in real life. We will be solving real life problems using the method that we have learned today. So I'll see you next. Bye.